Okay, the book has a good discussion about the differences between mutexes and the semaphores and the condition variables. Without mutexes, condition variables doesn't work as you see. Okay, without mutexes, condition variables does not work. Okay, if there are no questions, I will continue. Okay, it looks like with the spin locks, how did we start it? We looked at the locks, right? Spin locks. Okay, spin locks were good for the mutual exclusion. And with the Peterson's algorithm, we solved all the race condition problems. But the problem with the spin locks was that, what was the problem with the spin locks? It was wasting CPU time, right? It was wasting CPU time. So we did not like it. Sometimes we didn't like it, sometimes we liked it, but most of the time we said that it should block the process and let the other processes run when we are waiting for a lock. Okay, that was the problem. Then we invented semaphores, downwards counting mechanisms, and we said that there are specialized versions of the semaphores which are the mutexes. We talked about the mutexes, and with the mutexes, if I need to set some kind of a condition like the buffer is empty or not, we talked about the condition variables. Okay, these are the three things: spin locks and semaphores, mutexes, and condition variables. These are all good, they are all solutions, but they are difficult to use. Okay, they are very difficult to use. For example, the book has a very good example. It says that the book says that book says that if you reverse the order of these two, okay, get the lock first and check for the condition variable. Do the other way, check for the condition variable and try to get the lock. You will get into some kind of a deadlock, which is not good. So what I am saying is that making a mistake with the semaphores and the mutexes and the condition variables are easy. So they are difficult to use. Testing it is difficult because it is very difficult to test these kind of multi-threaded applications or multi-process applications because it is all timing dependent. The errors are not reproducible. Once you get an error, to get that error, running it just once does not work. Okay, you have to run it many times, and it doesn't. You don't get the same error all the time. It depends on your timing and everything. So people said that let's make something easier to work with. So they invented these monitors. Okay, they say that let's get help from the language itself. Okay, a programming language construct. They are very like, okay, these are invented in 1974. Okay, 1975. So they say that monitor is like a class, a regular object-oriented class. Okay, but only one thread can be executing in it at a time. Okay, they are like a class, but only one thread can be executing in it at a time. You have a class. Inside the class, what do you have? You have many methods, right? So only one method can work at the same time. And mutual exclusion is achieved this way. In other words, they are language implementation of mutexes. Okay, the language itself helps you implement this mutual exclusion mechanism. Okay, they are called monitors. Look at an example in a hypothetical language. This is not a real language. Okay, consumer-producer problem. Only either the producer or the consumer can run at the same time on the same object, even if you are using multiple CPUs. Let's ignore this for a while and let's look at a real example in Java. Okay, so Java is like an endless language. You will never learn the whole language itself. And today we are going to learn this synchronized keyword. Okay, Java has a keyword called synchronized. Okay, it's called synchronized. When you put that keyword on at the beginning of a method or a function in C++, but we don't have this keyword in C++. When you put this keyword in front of a function, only one thread or process can run that method at the same time. No two processes can run that method at the same time. It is synchronized. Okay. So let's look at the example actually. This is the monitor in Java example. There are 4 classes. One is the upper level, highest level class, this one, the producer consumer. Okay. It's a class, and we have 2 nested static classes. Okay. See, this is a static class producer, and it's a thread actually. And in order to run a thread, in order to write a thread, you need to write your run function. Okay, this is your producer thread, and inside the producer thread, you have your run function, run method, and this is a function for producing an item. And what else? We have another class here. It's for the consumer. It's very similar to producer. And we have our monitor class. See, it's a regular class, nested inner class, static class, our monitor. It doesn't extend from anywhere. So it's not a special class for the Java. But inside this class, we have this method, insert. Okay, we have this method, insert, and it is synchronized. What does synchronized mean? If consumer or producer is running this method, only one of them can run it. Okay, and we have another one, remove. Okay, is synchronized again. So Java knows how to synchronize these 2 methods. Only one of them. Okay. Only one of the processes can run these methods. It's kind of mutually exclusive methods, mutual locks or spin locks, if you will. Okay. So let's look at the details of this program, Java program. Okay. I have n will be used for the buffer size, okay, and I can produce at most n items at the n items can exist on the buffer at most. Okay, I have a producer and I have a consumer. Okay, 2 static references, and I have my monitor. Okay, our new monitor. Our main function, main method, it starts P and it starts C. Where does start come from? P does start. Who defines start?
Thread.
The thread library, right? So the thread class defines start method, and I call start method. Start method calls run. Okay, inside that producer. Okay, this is run for the producer. It says, okay, I have an item, while true, it produces an item. We don't care what it does inside this method implementation. I produce an item, and I insert that item to the monitor. Okay, to the buffer actually. So the inserting an item to the buffer is done by the monitor. Okay, inserting an item to the buffer is done by the monitor. And remember that insert was synchronized. Okay, insert was synchronized. So remember what was the problem with the semaphores and the mutex and the condition variables? It was difficult to use because you need to be careful with the order of the mutexes and the condition variables and etc. In this case, what I am doing is that in my producer example, I produce the item and I just call the insert method of the monitor to insert it. So the rest of the complexities will be handled by the monitors because I don't need to be careful about the getting a mutex and doing that kind of stuff. Okay? Yes.
Bayağı true yapmış ya. O ne zaman false olacak? Ne zaman çıkacak o bayağı?
It doesn't. It never stops. There's a producer-consumer example that never stops. Some producer always produces, and consumer always consumes. This is not the first time we are doing this. We did this many times. Okay, this is an infinite loop. Yes.
Hocam, biz mesela fonksiyonu küçük critical section istiyorsak öyle bir şey yapamayız. Yani bütün metodu yapmak zorundayız.
Okay, so you are saying that the whole method has to be mutually exclusive. Okay, between this line and this line, it all has to be mutually exclusive. In this case, yes. If you put that synchronized keyword at the beginning of the method, yes. But if you want only a small portion of your code to be synchronized, then you put it in a block, and at the beginning of the block you type synchronized. Yes, you might have synchronized code blocks in Java. That's fine. You can do it. But that's a Java implementation issue. Monitors doesn't have to be that way. Okay, this is the producer, and consumer is very similar. In an infinite loop, from the monitor, from the buffer, I remove the item and I consume the item. Consumer item is something irrelevant to us, so I will not look at it. So let's look at the monitor now. We have a buffer of size n, integers. Okay, and we have our counters, low and high. We will look at them, what they mean. Okay, we will look them. Okay, actually we can do it this way. This is our buffer. Okay, there are n elements. Low is the beginning of the full space of the buffer, and high is the, okay, this is low, this is high. Okay, so these areas are all full, the rest of them is empty. So when you put one more thing, it is in the high, becomes like that. Okay, the nice thing is that when I put another item here, okay, let me do this. When I put another item here, okay, and another one there, then high switches back and it does that. So it's a circular buffer actually. Circular buffer. So it is implemented that way, so that when I am at the end of the buffer, I circularly go back to the top. Okay, synchronized, void, insert. If count is n, that means that I have n elements inside my buffer, then I can't insert anything, so I go to sleep. And we will look at what go to sleep does. That basically go to sleep is for sleeping this thread, so that the consumer can produce some items and count goes down less than n. Okay. Otherwise, if count is not n, then I put my produced value to the high position of the buffer. Then I increment high by 1 and take the modulo of n and put it in high. You understand this line, right? This line? So it is used for the circular buffer. If this place is full, then I need to go back to the top. And I increment count by 1. And if count is 1, I will call notify. Notify means that if somebody is waiting on this object, to buffer to be available, okay, to buffer to be available, to item to be available, then notify all of those shells or the processes. Remember notifying Java? Where did we see notifying Java? Class object, right? Remember class object? Class object has how many methods? Class object has, tell me the class object.
Hash.
Okay, here. Object, class object. Okay, equals,
Clone.
you know that clone, protected, right?
String.
Hash code.
String.
Who is the brother of the hash code? Equals and hash code are brothers, right? Clone, what else?
String.
To string, what else?
Notify.
Wait and notify and notify all. These two, if I taught you the Java language, I told you that you will learn about these later, and I think the time has come. These two are used for synchronization. I think I mentioned it. These two are used for synchronization. Wait for is for waiting for the lock of this object. Notify means that this object is now available, now you can use it. Okay. So since, what else? Do we have any other methods or functions? Get class. Get class. What else? I guess that's it, right?
6 times.
What? Okay. So these are the basic object methods available to all the Java objects. So Java made this synchronization thing into the core of the very core of the class itself, class object itself. So wait, notify, and notify all are parts of the main Java objects. Okay. So let's go back to the example. Says that, okay, if somebody is waiting, okay, if somebody is waiting for the lock on this object, I am running on an object, right? Okay, I am running on an object. If somebody is waiting, remember that somebody called monitor insert, okay, monitor object. If somebody is waiting for this monitor object to be available, then notify them. And this one, go to sleep. Let's look at the implementation of the go to sleep. Here, the implementation of the go to sleep. It calls wait. It says that wait. Okay. It waits until what? It waits until somebody notifies this object, saying that okay, the thing is ready. Okay, the thing is ready. And the wait could come back with an exception. In that case, I would catch the exception and do nothing. So wait would just return, okay? Wait would just return after the wait, or it would come back with an exception. In that case, I catch that exception and I would just return. Okay. So two things. I either go to sleep, wait here, or I notify if somebody is waiting. This is for the insert method. How about the remove method? Remove method just does the opposite. If the count is 0, that means that nothing in the buffer is to consume. So it goes to sleep. It goes to wait. Otherwise, it gets the low, the buffer element at position low, and assigns it to the variable val, and it increments low by 1 and takes the modulo. It decrements the count by 1. If the count is n minus 1, what does that mean? If count is n minus 1, that means that the buffer was full and I consumed one of them, and now I can notify the producer. I can notify the producer so that it can continue. Okay. Again, this is synchronized. Okay. Any questions? So this is how we use monitors. In Java, you don't have exactly monitor, the keyword, there is no keyword named monitor in Java, okay? We don't have a keyword named monitor, but it supports object synchronization using this synchronized keyword in Java. Synchronized keyword, with the synchronized keyword, you need to use wait and notify. Otherwise, making something synchronized doesn't work, right? Making something synchronized doesn't work because you need to wait something. You need to wait something to happen. In that case, you wait, and if that thing happens, you continue, and you notify if anybody is waiting. Okay, you notify if anybody is waiting. Okay, so this is how the implementation of monitors happens in Java. Let's go back and read some more theoretical work. Okay, we still need a way to block if, say, the buffer is full. So in theory, wait and signal and monitors, they should, each monitor should have these two mechanisms, wait and signal. In Java, we have wait and notify. Okay, so there are different implementation of these monitors and wait and signal. The book talks about them. I will skip those. But in Java, each object may be used as a monitor. Okay, we made our specialized monitor class, static class, inner nested static class, and we made their methods synchronized. And methods requiring mutual exclusion must be explicitly marked with the synchronized keyword. That's the mutually exclusive region. Okay. Blocks of code may also be marked by synchronized as